All right, great, thanks. That was such a great talk. So, Michele Bannister, come on down. There we go. Okay. So Dr. Michele Bannister got her PhD at the Australian National University. She was a postdoc at Queen's University Belfast, which is where I first met you, I think, and a postdoc at the National Research Council of Canada, and now she is faculty at the University of Canterbury in New Zealand. And her main research is in looking at small bodies for galactic studies by interstellar objects. And today she's going to be talking about the impacts on satellites on our dark skies, which I'm very excited to hear about. So, Michele, I'll give you the clicker, and over to you.
Thank you, Carly. You have clicker. Excellent. So I'd like to transition at this point a little bit from this wonderful journey of exploration that we've been talking about. We've very much got an excellent idea at this stage of why we should explore, the ambition that we have and the goals that we'll be able to achieve in going to these outer reaches of the solar system. But I also want to talk here about the situation that we're in how we do this. So this is the observatory that I help look after in New Zealand, in Takapo in New Zealand, South Island. And you can see here the beautiful landscape that we have. And I want you to think about the way in which that extends above the beautiful landscape into the atmosphere, into the upper atmosphere, through the Kármán line, around 80, 100 kilometres, and into that near-Earth environment, through to, let's say, a few hundred kilometres, so kind of 200 to 600 kilometres for low Earth orbit. And in this region, you can think of this really as an environment, as a place where it forms a contiguous whole in the kinds of ways in which we explore through it and the ways in which our exploration vehicles end up affecting it. So it's not just something where you think about the environment as being a place where it's the near-Earth space or it's the atmosphere, and that these are entirely separate concepts, and we treat one of these over here with atmospheric physicists and one of these over here with astrodynamicists and space weather folks, and we should never talk to each other. This is something where, as we start exploring, we actually need to think of this as a unified community. So this is something where we have a lot of guidance in how to do this from bodies of knowledge that have been accumulated over time. So if I then start showing you what the sky looks like from our observatory, you get an idea that you have the orbital environment as something that is also connected to the optical sky, and the radio folks will be very familiar with this as well. But as we start going into the dawn here, we can really start to see the way in which the day and the night and the landscape and the sky are all connected. And I really like as a New Zealand scientist, the way that we connect the older knowledges of our communities and our landscape together. And we have a beautiful whakatauki, a proverb for this. And, sorry, we're getting something slightly different down here from what's up here. Excellent. And in Te Reo Māori, it goes, tuia te rangi, tuia te whenua, tuia te moana. And this one then goes into the people. Tuia ke te haere tangata, e rongo te po, e rongo te ao. Weave together the tapestry of knowledge that we have from the heavens, from the landscape, from the waters, from the people, so that we understand the day and the night. And I think this is something that we really want to take into understanding our near-Earth environment. So the way in which we explore is, of course, with our rockets. And this is something that we then have to start to think about, what are we using these rockets for? Because in order to enable all of this, we need these rockets. But the pace of industrialization that we're seeing in the near-Earth environment is also using these rockets at a rate that we have never seen before. And there's a thing that goes with this. The technology that we use, it can be thought of as a charismatic technology. I understand this clicker is going to respond. Come on, clicker. Yay, okay. We have the technology. And when I say it's a charismatic technology, I mean something very specific by this, which is actually inherited from computer science. The one laptop per child policy started talking about this in this context. And I think this is something we can really use in aerospace as well. A charismatic technology is one where the aspiration, the goal that we have of how we're going to use it, where we're going to get to, becomes the overriding factor in making any other decision about how we go about things. The means are justifying, the ends end up justifying the means in every way. And this works to some degree. But over the last 4 years, I've started to deal a lot more with the challenges that come with when this is put into tension. What do we do when the thing that we love, the exploration, starts to even damaging the thing that inspired us to go about doing this in the first place? So this is where we're at in terms of thinking about the rate of space industrialization. So on this side, we can think about the launch rate that we have going on per year. And on this we can think about the number of satellites. So let's first think about the launch rate aspect of this. Yep. We do have a change in slide that will work. There we go. Lovely. So together with atmospheric chemist Laura Revel and our master's student Tyler Brown, we've been looking at the way in which you have the effect of rocket launches on this environment. So the thing about a rocket launch is that you're depositing particulates into the stratosphere. As you burn your fuel to get your thrust, you're providing that material in a column up through the atmosphere. And this makes it very different from, say, flying an aircraft, because you're providing this material up in much the same way as, say, a stratospheric volcano does. So Hunga Tonga Hunga Ha'apai was able to do the same kind of effect. So we have natural processes that can do it on some time scale, but we're looking at doing this very routinely from our spaceports. And the thing that you'll notice here is the spaceports are particularly in the northern hemisphere. So we're also creating our emissions products in a very particular way as well. So we've quantified this, and we did so for 2019 because this was the last year that we had before the pandemic disrupted launch schedules quite a bit. And the emissions products that you can quantify from this are the things that you really want to consider. So the carbon dioxide, the water vapor, these are things that in the right locations have some effects, but when you put them in the stratosphere have very different atmospheric repercussions from the kinds of things that we talk about with normal climate change discussions. In particular, the alumina and the black carbon products and the chlorine act as reactants that can affect stratospheric ozone. So this is the thing where we end up going, okay, 2019, there's not that much of it. But we know this is the regime that we're not going to be in for long. So what are the future impacts? We don't know what the launch rate is going to be. We know it's accelerating, we know it's doubling, but we don't know where we're going to get to in the 2030s. But we see a lot of industry drivers that we want to accelerate this as much as possible. We don't know the effects of the new fuel types, the methalox, things like this. And we don't know all of the stratospheric chemistry that we need in order to be able to understand how this is going to react. But we can work this out together, I think. But it's going to take a while. So let's go back over to what the satellite side of things can do here. This is the current state of the near-Earth environment as of last night. This is the view of it, as you would see, considering it by perigee, so closest approaches here. And what we have is an environment where we've got to a point where the number of satellites has increased to the stage where we've got a very dense population developing in low Earth orbit, a little bit in upper low Earth orbit, and not so much in the geostationary area where you might have traditionally had a lot of these satellites. So the build-outs of these are... this is 1960. This is getting closer to today. The build-out of this has accelerated a lot in the last decade, and in particular, the last 4 years. So we're now at the point where we're looking at significantly more satellites that we've put into orbit around the Earth than we have exoplanets known, and we're at about 40,000 little pieces of tumbling material. So for those of us thinking about transient observations, this is where you can think about your glittering background starting to surround the Earth, and your deliberate emplaced background that's starting to arrive as well. And the thing is, this is a process where these are accelerating, and we're looking at 17 or so major constellations going in sometime in the next decade or so to a maximum potential population. Good estimates are around 100,000 or so satellites. This will change. There's a number of various geostate operators involved, but this is also something that has to be replenished because these are low Earth orbits, so they're coming back down. Again, we don't know the effects on the stratospheric chemistry of that deorbit and the ablation that you get to burn them up in the atmosphere. These are things where it's being made in a state that requires constant replenishment. So we can think about this in terms also of what we actually see in the sky part of our environment here. So to remind those of us who don't think about reflected light quite so much, we have our nice view of the night sky on this side of things. And when we create artificial light, or say if we're creating radio sources, we're emitting that and diminishing the brightness of the sky that we can see as a result. But the satellites are sitting up above that darkened region, so they continue to catch the sunlight and to be able to be visible from any site within the Earth's shadow. And they'll also be emitting in the radio, so you get these side lobes coming over and painting the Earth's surface. So the question then becomes, what do we do? Well, at least at this point, we're looking at, for an estimated constellation build-out, for instance, Rubin is looking at having a satellite streak in pretty much every image. And you have to look at maybe a 10% time sacrifice if you were going to try and drop that twofold, which is a lot. We're also at a stage where the scale of these satellites is changing rapidly. So this is, for instance, the prototype that we have called Blue Walker 3 that went up about a year and a half ago now, and there's meant to be about 600 or so of these, and as you can see, it's quite a substantial 64 square metre object. And this made it, as we measured with a set of telescopes around the world, this made it one of the 10 brightest things in the night sky. So, yeah, it was sitting in there at first magnitude, and the observations here from New Zealand were made by a very capable master's student. So that kind of brightness is something where, on the focal plane of our beautiful Rubin camera detector, is going to be quite substantive. And this is where it really starts to come into the foreground that industry are creating for the kinds of issues we're thinking about with transient detection, with astronomical detection. All of these networks and all of this situation that we're building are going to have to cope with incredibly bright streaks, with image artifacts, with glints, with flares, with clustered flares. The streaks don't just stay constant. This is a simulated one for the Rubin detector. They actually vary a lot along their length and in the width of their point spread function as well. So we're looking at a situation where you end up with quite systematics limited science for all of this work that we've put in. And this is quite something when you consider also that, I'm talking here about the optical impacts. The radio impacts are just as substantial in many ways from the overlapping side lobes. And it's not just a large grand-based sky survey problem. For instance, in New Zealand, we've had a cultural renaissance recently for the Māori New Year, for Matariki. And this is the commemoration and celebration of the heliacal rising of the Pleiades, the cluster known as Matariki in New Zealand. And one of the things that we have with this is something where tens of thousands of people go out before dawn to watch the cluster in the sky and to undergo practices of family and community in connection with the environment that have taken place for thousands of years in New Zealand and across the Pacific. And so this is last year. You can see a full train of Starlinks going across on orbit rays. This was actually just as they finished the ceremonial aspects of the dawn. And at that stage, one of the local astronomers, Victoria Campbell, was describing these of satellites as knowledge blockers. So what can we do? This is a situation where the community has been thinking about this to some degree. On the astronomical side, on the industry side, as they were made aware of the impacts that were going to occur with these particular plans, and on the policy side and the governance side as well. So it really has stemmed from, okay, let's see what the issues were. That was kind of the phase through late 2019, 2020, as everyone scrambled to go, how bad is this going to be? And then we really started getting into what are the pathways that we have for being able to make changes, make recommendations, start to get industry to mitigate the brightness of their satellites, start to put time into developing brightness mitigation solutions, radio quietness solutions. And this has, I think, gone in two very promising ways. One is that it's very actively discussed now at the UN Committee on the Peaceful Uses of Outer Space. So COPUOS is the part of the UN where these discussions take place at a multilateral effort across. And it is now an ongoing agenda item there, which has made a big difference. There's also a much greater understanding of regulation, I think, even from astronomers. We also have the Committee for the Protection of the Sky, which the IAU set up, and which is a kind of forum for all of these communities of policy and industry and astronomers to really talk about how to solve some of these problems. So by all means, come and have a look at IAU CPS. We always welcome people who would like to have a peek at this and get involved. And this is really the thing where it ends up being a community effort of what are we going to do about all of this? Because this is a challenge. There are an awful lot of competing interests of what can be done with the near-Earth environment and how we're going to go about doing it. But you can make progress on this. So this is the exact kind of challenge that I put to our space agency in early 2020. And in 2022, New Zealand Space Agency started putting together its first public announcement of the policy that they were then going to consider enacting and have consultation on as part of the development of New Zealand's first ever national space policies. And so you can get policy movement on this quite fast. And New Zealand has been very active at COPUOS in discussing space sustainability since. So I would say it really is a situation where there are a lot of opportunities to talk to industry, to say, how do you make a satellite fainter? How do you put that into the design process from the beginning? How do you go, what is the impact on your local community? What is the impact on the appreciation and the protection of the dark and the quiet sky? And for the launch providers, there are many atmospheric scientists who will be very happy to work on the modelling of the rocket launch impacts. We have the tools, and we just need some of the measurements of the kind of products that these things are creating. So there is a best practice that we can work towards. But for those of us who are creating the missions where we're going to go out and explore, this remains our problem too, because we are part of trying to make this. Thank you.
Thank you. Thank you, Michele. I think dark skies have been an inspiration to many of us in this room, so I think a lot of us felt very poignant through that talk.